Okay, hello. This is getting into some new material in section 5.2, talking about the definite integral. Working with the things that we've been doing up to this point, where the example that I did, like in my presentation for the area under the curve regarding um, the, the distance that the vehicle was traveling, or the idea that you have velocity on the y-axis and time on the x-axis. I'm going to go ahead and get us to the iPad and, and recognize now that what I'm going to be showing is how this is the definite integral, notation of the definite integral expressed as a sum of areas of rectangles. That's what we're talking about here. So the example that I had given was starting at 20 feet per second, and every 2 seconds there was a new measurement made. And the area of the lower end of this rectangle was down here. The lower end was, I would get the left side. Since it's increasing, the left side was always the lower end. It was the lowest part of the deal. So the sum ended up being lower. But the idea of adding these up has to do with this notation up here. Let me look at this up here with me. It says the limit as the max delta x sub I goes to 0. X sub I. In our situation, for this problem, our delta change in x is 2 every time. It's 2 seconds. The width of our rectangles is 2. So delta x sub I is 2 in our case. In Riemann sums, it can be at any value. It doesn't have to stay a constant. Okay, it doesn't. But in our situation, I think it's more clear just to picture it as it's always going to be 2 in this case. Well, then the height of the rectangle, in our case, is going to be the left-hand side where we're on the low end of each interval. Okay, we're starting here, and it's starting on the left-hand side, and that's determining the height of our rectangle. So that turns out to be this, the f of u sub I. The u sub I is talking about some value inside the interval, okay? Somewhere inside there. And ours in this case is the far left. It could also be the far right. It could be somewhere in between. But the idea is these are all rectangles. Delta x is the width, and f sub whatever it is you're working with is the height. And the width or the length, whatever, yeah, the width and the height. But the situation here is you're going to add all these together. And in our case, there were 5 of those rectangles, so n was 5. But the circumstance is that as the delta x gets smaller, n's going to go up. In other words, if our delta x went down to 1, then we would have 10. And our n would be 10. If it went down to 1/10, then it would be 50. You would have 5 of those 10s, and it'd be 50 of those. So n would be 50. And then as delta x sub I gets smaller, n's getting bigger. And then envision it yourself that as that goes to 0, the width goes to 0, n is going to an incredibly large number. And even to the point of, we're going to say, to infinity. And as a result, it's getting so narrow that it doesn't matter if you're picking a left or a right or some other point in between, because it's so small that f of the general value is going to take care of it. That's the height of the rectangle for anything you pick. So, and that means this x sub I is, delta x sub I is getting smaller and smaller. So you're repeatedly, these are the rectangles being added up, okay? And it's the sum of all those rectangles being added up. That's the area under this curve. And that is exactly what this notation designates. The delta x sub I is converted into this dx. The f of x is actually the value of the function at any point along the x. And in this case, the A and the B aren't really designated in this diagram the way this is listed, but it's on some interval from A to B, okay? So that's a key point I want to get across about where the integral symbol, the definite integral, comes from. They also call this the Riemann integral. He got credit for that. The Riemann sum is another way of saying the Riemann integral is a definite integral, all right? So that's the idea. You're getting the area under the curve. You're adding up all those rectangles and getting them tinier and tinier widths. And as a result, getting less and less air, and therefore it's becoming a smooth curve underneath the area. Okay, good. That's it for right now. And that's the general idea about where the definite integral came from.